Good evening. Hi students, welcome all of you. Welcome to this second session on FET and MOSFET and its analysis. Yesterday we have been learning about the basics of MOSFET, about what is the controllability equation, and if I'm live, just give me a small hint. I'm live. Yeah. So yesterday I was talking about the controllability equation, the transfer characteristic equation of JFET and MOSFET, and I was also talking about the various biasing circuits. Today's class I'll be talking about its AC analysis. I'll be talking about how do you represent a MOSFET or a JFET with its AC model, with its amplifier model, and I'll be showing you what is the input impedance, output impedance, voltage gain calculations of the MOSFET. So the agenda is essentially to teach the students the AC analysis. So before that, let's discuss about a few points. The most happening thing in Unacademy is the All India mock test series. Test series which is being conducted in lines of the GATE exam, and it will be there every Sunday at exactly at 3 o'clock in the afternoon, and it's every Sunday starting off with Jan 2nd to Jan 30. It's going to be there. So this mock test is the most happening thing. So do write this to know your status. Where do you stand by? What is your position in it? So it's going to help you a lot. And similarly, of course, offer on Unacademy subscription. If you go for 2 months, you get 4 months free. Additionally, that's a very good way to join for Unacademy subscription. And of course, 2 months, 12 months, 2 months free. And all this you can come through the compact exam. The compact exam is one of the best ways of joining Unacademy. Compact exam which happens every Sunday. But this week it's mega compact. So this time there will be 200 lucky participants. The general compact exam you have only 100 lucky participants. But this time it will be 200 lucky participants. And of course even 100% scholarship chance are there. All you have to do is to answer 20 questions in 60 minutes, exactly 3 minutes per question, the same standard that you maintain for GATE also. So that's all you have to do. Mega compact exam. And these are the upcoming batches. My Enroll shortly starting on 27th. And this is our team, the entire team you can see here. A team of ECE and a team of electrical. That's the team you can see. That's yesterday's class we had all about the controllability equation of MOSFET, the equations that control your gate voltage and the drain current, the controllability equations, and this is of course continuation of the simplest biasing technique, going ahead with the source resistance based biasing, then of course going ahead with voltage divider biasing. For all these things, we look at how does the AC model look like now. So today's class starts off with what will be your AC or amplifier model of the JFET or the MOSFET. That means how do you represent your simple circuit or a simple symbol like this into some sort of a circuit or some sort of an elements. The discussion is how does this circuit or this symbol get expanded into more circuit elements. For that you should know one thing, that there is basically the gate which acts as the input, there is a drain which acts typically as the output, and there is a source which is the common terminal for the input and the output. Gate and the source are totally isolated. Why is the gate and the source totally isolated? The gate and the source is totally isolated because it's mostly an oxide layer that is there in between. So you don't find any connection between the gate and the source because there's an oxide layer, or sometimes there is a reverse bias junction. If it is a JFET, it's reverse biased, or if it is MOSFET, there is an oxide layer. So you can clearly keep this open, but the drain and source, there is a current flow. So drain and source, obviously there is a current flow, and this current flow is not simply controlled by the VDD there. Given this saturation region of operation, this control here or the current here is controlled by the gate voltage, so that it is called as GM into VGS, and it does not absolutely depend on anything else. It does not absolutely depend on anything else. It depends only on this VGS. So if you look at your graphs, or if you look at your equations, if you look at your working of the MOSFET, we clearly say that in the saturation region, the VDS versus the IDS curve purely depends only on the corresponding VGS. For a given VGS1, I find an IDS1. For a different VGS2, I find an IDS2. So on, I find for a different VGS3, IDS3. So that my IDS is no way depending on the VDS, and it is depending only on the VGS. So practically the graph is expected to be parallel to the x-axis, and it is totally independent of VDS. But practically, because of early effect or because of non-ideal nature, this graph may converge somewhere. It is likely to converge somewhere. So therefore, the graph is not expected to be completely parallel to the x-axis. So we say there is a slight slope like this. There is a slope. This is what we call it as a finite amount of output resistance. So therefore, we cannot say that this is ideally being controlled only by VGS. There is also a non-ideal resistance. There is also a non-ideal resistance in the form of R0. This R0 can be assumed to be infinite, and this becomes ideal if your graph can be assumed to be parallel to x-axis, if your IDS is purely depending on VGS. But it practically depends on VDS also. The slope may be there, noticed, a slight slope may be there. So therefore, there may be a finite resistance also. There may be a finite resistance. So this forms your final circuit model. So between your gate, drain and the source, there is a flow. There is a flow between the drain and the source. This flow is being controlled by the gate. This flow is being controlled by the gate. Non-ideally, there is also resistance. This forms a circuit model. This is how you draw the AC model. So the AC model ultimately looks to have an open circuit between the gate and the source, seems to have a current source of GM into VGS with a finite resistance of R0. This is the drain. So ideally, if somebody asks me what is its input impedance, I will say it is infinity, because input between the gate and source is absolutely infinite. If ideally somebody asks me what is the current gain, I will say it is undefined. The current gain is undefined because there is no input current and gate is isolated, gate is insulated, so there is no current gain defined. But if ideally somebody asks me what is the voltage gain, yes, I have an answer. The voltage gain is nothing but the output voltage flowing across, the voltage across is R0, which is R naught into Gm into VGS by the input voltage VGS. So it is Gm into R naught. And if somebody asks me what is the output impedance R naught, that is also finitely the same, that is R naught. So you can say that there is an output impedance, there is an voltage gain, but there is no input impedance, there is no current gain. Practically nobody will ask you such things in the exams. Practically in the exams they'll ask you with biasing circuits. That means the model as it is independently may not be the necessity of competitive exams, knowing what the model is and what the parameters are. In most competitive exams, it's important for us to know what will be your input impedance or output impedance and voltage gain and such things, considering the biasing circuits. Considering the biasing circuits, anything like the voltage divider bias, or maybe considering the cell bias or fixed bias. So the loading effect of the bias resistance are very important. So if you look at the loading effect of each of these bias resistors, typically if you look at the voltage divider bias, that means if you look at the AC model with the voltage divider bias, here comes R2, here comes R1 between the gate and not the source, between the gate and ground. So therefore, if this is assumed to be the ground point, there comes R2 and R1 between gate and ground. That's what you can see here. R2 and R1 between gate and ground. Not between gate and source, gate and ground. Even R1 is coming because VDD will be short circuited. All DC sources will be short circuited. So R1 comes, R2 comes between gate and ground. What about RS? RS comes between source and ground. So therefore there comes RS. There comes an RS between source and ground. So therefore, practically with the biasing circuit, practically with the biasing arrangements, you will find a RS here, and you'll also find RD loading things between drain and ground. So you'll also find an RD this is RD, and this is where the output is being taken. So ideally speaking, your FET is as simple as this: gate, drain and source with an open circuit here, but practically with the biasing resistors, practically taking into account R1, R2. This is how things are changed. So that's very clear, students, that your input impedance is not infinity now. Hi Venkatesh, hi. So if you consider the input impedance, which was infinity without the biasing resistors, it is not infinity now. It is supposed to be R1 parallel to R2. So that you have to maintain an R2 and R1 very, very large, because here comes practically a signal with an RS and a VS. So that the input impedance is R1 parallel to R2. So that the voltage over here controls the current flowing through this. That's how the modeling has to be done with. Now suppose if it is not fixed, if it is not this bias, and if you are looking at a biasing circuit like self bias, then in the place of R1, R2 there will be RG there. In the place of R1, R2 there will be RG, and RG has got to be large enough so that the input impedance is not being lowered. Because it's an voltage control device, the voltage controls the flow here, you should have obviously a large impedance here, so that the voltage is not driving a current and being wasted. So input impedance is expected to be high because it's an voltage control parameter here, voltage controlling the output flow there. Similarly, if you replace your biasing circuit like voltage divider bias with your fixed bias or self bias like this, RG replaces your R1 and R2. That's how things work out. Got it? Now what about the voltage gain, or how do you calculate the voltage gain? The voltage gain can be calculated very easily. The voltage gain calculations are most often done by ignoring this R0. That is, if you practically ignore this R0, most voltage gain calculations are very simple. Considering R0 to be almost infinitely large, the voltage gain calculations can be done as simple as this, that the current flowing through the GM VGS also flows through RS and logically flows through RD also. So therefore your output voltage for the voltage gain calculations will be GM into VGS current flowing through the RD by the input voltage VGS. So logically it is GM into RD. So simple as that. So FET model as per the AC analysis makes it quite easy to analyze. You can't get any tough questions for any biasing circuit, even if there is RS or without RS, provided we can ignore the R0. Sir, what if I can't ignore the R0 and if I have to consider the R0 also? If you have to consider the R0 also, you have to take the current division rule applied. You have to find out the current dividing in these two branches and find out what is ultimately the current flowing in it. And obviously, the current flowing in this will be GM into VGS itself. So even if R0 is considered or not considered, it doesn't affect your final answer. I hope this is very clear, students. I hope the point is clear. So AC analysis always involves four things. Every AC analysis involves calculation of AV, input impedance, output impedance, and current gain. The good news is this will be almost infinity if it is only the MOSFET or the JFET, or it will be equal to the RG, or it will be R1 parallel to R2. This will not be defined because IG will be 0. Input current is 0. So you will be left out with only AV and Z0 calculations, output impedance and voltage calculations. And for voltage calculations, all you need to do is to ignore this R0, and know that the voltage across this output is nothing but the current flowing in this branch, which is GM into VGS multiplied by RD divided by VGS. As simple as that. I hope you got the point, students. So that's about the AC analysis. So whatever biasing circuit is, this is the way of doing it. Doesn't make any difficulty more than this. So see you students in the next class on BJT in the same way with revision. Bye students.